one announcement, milestone number 3. Okay. Milestone number 3 is due on Wednesday. So, please note, and I emailed you regarding this, milestone, right? And this time I'm providing reference design, right? Look at this one. I'm providing reference design. So it will be pretty easy. Reference means, solution, right? Even solution. So, but, thing is, do not copy the solution, right? So think first and write, design your own, hardware on top of this skeleton design, okay? And then probably if you run into some problem, compare that with this reference, right? That would be better approach. Okay, any question about milestone? By the way, if you have a webcam, please turn on. Right? I feel like turn on. All right, thanks. Okay, let's get started. Last time, remember we finished single cycle CPU design. That is the last, the one, right? Last design. And if you look at this, we are able to design almost all hardware component in this CPU. Look at this, register file. We designed a long time ago, right? And sign extension, piece of cake, right? Adder, right? Just to use, plus operator, plus in Verilog. Multiplexer, easy, right? Program counter register, adder, multiplexer, almost all the hardware component except these two, control unit and ALU. Control unit, ALU. We'll talk about these two today. Okay. Before that, let's go through some, example instructions, how those instructions get executed in single cycle CPU. Take a look at. Let's go through some examples first. This one, Sujin, can you please?
Single cycle RISC-V. Again, keep in mind that microarchitecture is composed of two interacting parts, data path and control. Let's execute some example instruction on what we have designed so far. Then we are going to design control logic in detail.
Okay, thanks. Let's take a look at this. Let's execute this instruction, memory read instruction, LW. So thing is, we want to read from memory location 80, right? 0 plus 80, and then store that value into X2 register, right? So first step in instruction execution is instruction fetch. So program counter is providing memory location, and that location, at that location, that instruction is there, right? So you are reading LW instruction, and that is inside the CPU. And next step is decoding, right? Decoding two things. Source operand preparation. Okay. So first source operand 0 is coming from register file, which is 0, right? 0, hardwired to 0. And second operand is coming from immediate. So going through sign extension logic provided to ALU. Right? ALU is doing ALU compute memory location. And second thing, decoding stage, right? Second thing is what? Control signal generation. So in this simplified block diagram, there is control signal, right? ALU source. Which one do you want to select? The one from register file or from immediate, right? So one means you want to select the second one to ALU. Okay. So there is decoding stage and execution step. Execution step. What should be done? ALU is computing memory location by doing addition. 0 plus 80, right? 0 plus 80. Memory location is provided to this data memory, and data is coming in, right? And control unit, control signal is generated, right? this control signal was generated in the decoding stage. So one means what? One means you want to select second input, not ALU output, right? This memory data to register file, because it is LW, memory read instruction. Okay, that is the one. Okay, then this data is written to register file, right? That register, destination register number, right? Then next step is PC plus 4, right? The program counter is incremented by 4, right? By hardware, by CPU. Okay. So assume that next instruction is store word instruction, memory write instruction. The same, same thing happens, right? From new okay, animation to animation. Okay, so from memory location PC plus 4, CPU is reading SW instruction. Okay, coming in. Then decoding stage, source operand preparation, right? 0 from register file, and 84 immediate from sign extension logic. Okay, so ALU is doing addition to compute the memory location. So output will be 84, right? 84. So from location 84, writing this data X2, store word, right? Memory update instruction. So X2 is provided from register file, second output, the first output, second output. So data is provided from register file, and memory location supplied from ALU. Okay. So how about data processing instructions like addition, subtraction, and or XOR? Okay. Arithmetic and logical instructions. Then same thing, right? So instruction fetch. Then these instructions is following this path, right? Reading instruction from memory. Then in this case, R format instruction. Okay, R format instruction, meaning two source operands are coming from register file, right? Two source, not I format instruction, right? Example is add I case. For example, right? First source is coming from register file. Second source is coming from immediate. Okay, I format instruction. Whereas this one, these are R format instruction. Okay, meaning RS1, RS2 are coming from register file. Okay, so it is pretty easy, right? So supply source operand to ALU. ALU will do, in this case, addition, in this case, subtraction, and or XOR. Then output is following this path. Okay, following this path. Multiplexer should select first input. So control unit, right? Control unit will generate the control signal by looking at these instructions. By looking at this, okay, I know this R format instruction. So mem to reg control signal supposed to be 0 to connect ALU output to register file. So easy. How about BEQ instruction? Little bit complicated, or so BEQ instruction. Okay, the first step, instruction fetch. Okay, instruction fetch. Then so take a look at this instruction. Okay, is it I format? No, it is. This is wrong, right? It is not I format instruction. So BQ. So first source, second source, right? Supposed to be what? Is it I format? RT. No destination register, right? So let me check. PQ. Key type instruction, right? So that is I need to fix that problem. Okay, B type. Okay, sorry about that. BQ. So B type instruction, meaning two source operands are coming from register file. Okay, the source operand. And then what should happen inside the CPU? Two things, right? BEQ, X3, X4, X5. Label 1. So first thing, branch destination. Right? Destination location. Right? That is PC plus what? Sign extended immediate. That is destination. The first thing. Second thing is what? Branch resolution. Taken, not taken decision. This one is taken branch or not taken branch. For that, you have to do probability subtraction. CPU should do subtraction to figure out, taken, not taken, branch decision. So, first, branch destination computation. Destination PC plus sign extended immediate addition, right? PC is provided. PC is provided from here, connected to this adder, and sign extended immediate. Okay, so adder output is branch destination. Okay, then this control signal be taken. Be taken will select either first input. What is first input? PC plus 4. Right? PC plus 4, or this one is what? Branch destination. So depending on be taken control signal, CPU will select first one or second one. Okay, who is generating be taken? This one. Okay, this one be taken. So BEQ, if you remember, the last design, BEQ, BEQ, so branch, right? Branch control signal is generated from control unit. Okay, this one is coming from control unit, and zero output, meaning these two are equal. ALU will do subtraction. Subtraction. If the output is equal to 0, okay, meaning these two are equal, that output 0, ALU output, ALU output, the 0 will be 1. Okay, 1. So that means then 1, right? So if instruction is BQ instruction, BQ, and this control signal is 1, then it is taken branch. Right? So taken branch 1 means it is this multiplexer is selecting second input, right, to program counter. Okay, like this. Okay, so animation. So ALU will do subtraction, should do subtraction. Okay, you have to ask ALU to do subtraction, right? By generating control signal. Okay, so microarchitecture again. Microarchitecture is again composed of data paths and control, right? So you are paving all the paths. You are paving this path, okay? This path where data is traveling through. Okay, so that is hardware design. You are paving that path, okay? Paving the highway, right? This highway, right? This path, sorry to be path. This path all the data paths. Data is traveling through. Then you have to control the path. So example is this multiplexer. Which path you have to take in case of addition instruction? Okay, you have to take this path. The first input to this ALU input. Add I instruction, I format instruction. Which path you have to take? Sign extended immediate to this ALU. You have to take that path. So by using this control signal, By using this control signal, you can do that job, right? Do that job. So control signal is, as the name implies, control is controlling data path, right? So control data path, which path you have to take. Think about the railway. Right? If you want to travel to Busan, right? From Seoul to Busan, right? Busan. Then the trail, right? Train is traveling, train is following, travel is traveling to, Daejeon. From Daejeon, it is separated. So either go to Busan or go to Gwangju, for example, right? So someone supposed to control, right? Control that path, right? So all the path is already prepared. So depending on your destination, you need to control, this control signal, right? So same thing, right? So CPU, all data paths prepared, right? So then, depending on the instruction, then you can just control the paths. Very simple, right? Any questions so far? Okay, let's move on. Okay, now let's talk about this control signal generation. And ALU design. Okay, so these only two hardware modules remaining, right? Then we are done. Okay, this one, Yeonjae, can you please? Okay, Herim. Okay, 영호, 김영호.
Control signals derived from OP code Funk7 and Funk3.
Okay, thanks. Control signal. Okay, these control signals. These control signals are generated by looking at this operation code. Right? By looking at this operation code, you can tell what kind of operation CPU should do. Right? Addition operation, subtraction operation, and or memory read, branch. By looking at this, you can generate all these control signals, right? So by looking at these three, operation code, right? This one, function 7, function 3, okay? So, control signal generation. So how to, design this control signal generation module? So in hardware design, there is no specific rule. So you have to use your intelligence and imagination and creativity, to design, hardware. Right? Same thing goes to software, coding, right? For example, sorting program. Think about you are writing, sorting program, and probably you are thinking about, okay, what kind of algorithm you want to use? I have to use quick sort, bubble sort, insertion sort. What would be best algorithm for our application? Then you have to use, if the algorithm is selected, then you have to use your brain creativity to write, neat, very nice code. So depending on your, style, or, some the coding style, the performance, the execution time of your program would be different. Same thing goes to this hardware design. There is no rule. So we have, only principle, hardware design principle. What is that? Combination logic design and sequential logic. That is the principle, right? And we know how to design combination logic, how to design sequential logic, right? So that is a principle. Based on that principle, you have to use your brain, your intelligence, okay, and creativity, imagination, right? So I think in control unit design, I think it is making sense to separate control unit into two parts, like this, two parts. The first one is main decoder, second is ALU decoder. So that is control unit I'm thinking of. So you don't have to, if you don't like, okay, you don't have to follow this, this design. You can use just one big module. You can design one big module if you want. Okay, but I think it makes sense to separate control unit into two parts. The reason is, ALU control signal. ALU control signal is different depending on this. Okay, but all the other control signals, you don't have to look at function 7, function 3. If you look at the encoding, look at the encoding, then you will figure out, okay, all these control signals except AL control can be determined only by operation code, this OP code. So that is the reason behind why I separated control unit into two parts. Okay, all control signals are generated based on this OP code, except this one. Okay, so that is the the reason. So let's first before we talk about this design, okay, let's talk about ALU design first. Okay, ALU, okay, meaning this one, this ALU design first. Okay, then we will talk about how to generate those control signals, including ALU control. Okay, ALU control, ALU design itself. Okay. This one also, same principle. There is no, rule. Okay, you have to use your intelligence to design ALU. And I think this one is more pretty intuitive and simple hardware design. And that design, take a look at this schematic diagram. This design, okay. So what is this? What is this one? Hardware component. That is multiplexer, big multiplexer. Okay. So that means depending on this 4-bit ALU control 320 4-bit, you are selecting either first one or second one, third one, or last one to this output. So that is 4-bit ALU control 4-bit is used, this green part, okay, green part is used to select correct output out of this 9, 0, 1, 2, 8, 9 inputs. Okay, then what is this component? This one is adder. Okay, this is AND gate, OR gate. So this one is for AND operation, AND, right? Because RISC-V instruction is providing AND, right? AND instruction and I instruction, right? And that OR gate is there because RISC-V has or I instructions, right? And this adder is there to do addition operation, subtraction operation, add I instruction execution, right? Okay. So if adder design seems to be a little bit complicated. This is adder. Okay. That component is able to do addition and or subtraction. Addition or subtraction. How come? Let me show you. Let me design adder and subtractor. Adder, subtractor. Okay, from scratch. So adder means what? Adder means you want to do this kind of operation. Y, A plus B. That is adder. Subtraction, Y, A minus B. Right? So in computer, the subtraction is done with the addition using 2's complement notation, right? So this subtraction is done with this one, minus B, right? What is that? Minus B, we are using 2's complement notation, right? That means you need to do flip all the bits and add 1, like this. Starting from positive B, flip all the bits, then add 1. So compare that. Compare addition with that subtraction output. And somehow, right? So that is why subtraction operation is done with addition in computer, right? So then the question is, we want to use one adder, just one adder to do this one and this one. Okay. So then we have 2 inputs. So what kind of circuit, what kind of digital logic circuit you have to design for these 2? So let me write down here, A plus B. So if you compare these 2, so depending on operation, these 2 are different. And also, you can think there is 0, right? So these 2 are different. Okay. So first source operand is directly connected to adder, and second source B or inverted B, depending on okay, addition instruction, you want to do that operation. Subtraction operation, you want to do depending on instruction, you want to create B or inverted B. So second ALU input supposed to be different depending on instruction. So we can place multiplexer. So B or inverted B. This bubble means inverted, right? This bubble means inverted. If you are confused, then just use inverter, right? Like this. Okay, B, normal B, and inverted B. That means inserting in a multiplexer means you need control signal. Someone should provide control signal depending on instruction, right? So what's remaining is this one, 0 or 1. Okay. Plus 1. For that purpose, do you want to use separate adder for that plus 1 operation? No, that is waste of hardware. Instead, we want to use this carry in, right? Carry out. You have carry out. Okay. In decimal addition, right? You think about this. 5, 7, 6, right? Example. So to add this column, you need to know this carry in. This is carry in. Okay. Carry in is 0, right? In this simple case. So by considering carry in, you add these 2 operands. So 9. So carry out is generated, which is 0. Then you do addition 9 and same thing. So that carry in, right? So carry in. So depending on instruction, you want to supply 0 or 1 to carry in. Okay. So that means what? That means you want to use multiplexer. Or if you use your brain, you can simply use sub, for example, sub control signal, 1-bit control signal, sub. If subtraction instruction coming in, then that will be 1. If addition is coming in, that control signal will be 0. How about that? And also, how about this? This one can be connected like this. Okay. Subtraction instruction. Subtraction is coming in. Then multiplexer will select second input, inverted B to adder. Okay. So this design is this one, right? This design, adder subtractor. So in my design, I use MSB, most significant bit in ALU control signal, okay, to select multiplexer and to provide this carry in. Okay, so look at this. So that is the encoding I assigned. This encoding ALU control 5 zeros. If those instructions are in CPU, for those instructions, addition, add-I, load, memory read instruction, LW, for example. Store instruction, SW. You have to use ALU, right? To do addition operation, to compute the memory location, right? So for those instructions, I'm going to generate that control signal. Okay, look at this. Subtraction instruction. For subtraction, if instruction is a subtraction, then I'm going to generate that control signal. 1, 4 zeros. Meaning what? 1 means what? 1 means a multiplexer will select inverted B. And carry in will be 1. Right? Carry in will be 1. This one. And at the end, right? This one, last 4 bit. This big multiplexer will select this ALU, adder output to this Y. Okay, in case of subtraction instruction. Same thing goes to branch instruction. Branch, right? For example, BEQ instruction. BEQ, do I have? Oh, okay, branch we have here, right? BEQ, PLT, for example, and some more, right? X3, X4, X3, X4. Then label 1. So you need to compare these two source operand. How to compare? By doing subtraction, right? Same thing goes to here, right? By doing subtraction, you can compare which one is less than, which one is smaller. And the first one is smaller than second one. You have to do subtraction first. So instruction is branch. Then I'm going to ask ALU to do subtraction. So you should generate that control signal. Control unit, right? Control unit should generate that control signal. And look at this, set less than, SLT. If you remember SLT instruction, SLT, set less than, X3, X4, X4, X5. If X4 is less than X5, then that will be 1. Otherwise, X3 will be 0. Okay, set less than. So comparison, right? Like branch instruction, comparison. So instruction, that instruction comes in, then control unit should generate that signal. What is that? Meaning 1 means what? 1 means this one, adder, right? This mux selection and carry in. And the 4 bit 0, 1, 1, 1, 7. So that means okay, so I don't have that logic. I don't have the logic 0, 1, 2, 8. So I have a logic. I have that logic for cell less than unsigned. Okay, 1 3 zeros means what? 1 3 zeros, 8, right? 8. 8 means you want to select that output. Okay. So unsigned, cell less than unsigned. This one is pretty easy compared to unsigned number comparison is pretty easy compared to signed number comparison. So in case of SLTU, you think of these two as unsigned number, unsigned, right? And in case of an unsigned number, if you look at this carry out, then you can tell which one is smaller. But signed number comparison, you have to look at other flags, overflow flags, right? So this adder, remember? I think I left it to you, right? Carry out and adder will generating overflow flag, zero flag. Zero is that zero flag, right? And also negative flag. So by looking at for signed number comparison, by looking at overflow flag, and this one, you can tell which one is smaller. I left it to you because it takes time. I assume you have taken digital logic design course. And this schematic diagram does not show everything, right? So it is showing only adder, addition operation, right? Logic, adder subtractor, and or, and last SLTU. So for these instructions, shift instructions, you have to add some hardware component. And I assigned those control signals for shift operations. Okay, so that is the control signal I assigned. ALU control signal I assigned. Okay, but if you don't like it, again, you don't have to use that table. Okay, you can create your own ALU and then control signal if you don't like it. And then so once let's design first. Let's design ALU first. So how to design ALU? It is very simple. Let me use full screen to show you to use pen. Full screen, hopefully. Okay. So this is an example. Example design, CPU design. And highlight, yeah, highlight is better. Which color? About, okay. Okay, so take a look at this one is pretty, so I'm trying to write this design, okay, this design in Verilog. So look at this. For example, this one. What do you think? This always statement is correspond to what? To thick. That is corresponding to what? It is covering what? It is selecting, right? Case statement. So depending last 4 bit, ALU control. Okay. So you are selecting either sum or AND gate output, OR gate output, SLTU. Otherwise, you are providing 0. Okay. So that covers what? That covers This one, and it covers adder. No, it is not covering that adder here. Until that, okay, this one. Okay, and we assume 32-bit adder. 32-bit adder is provided in the library, or you can design it yourself, right? The reason why I created my own adder is because of this output. I want to generate this ngCB output, these flags, in addition to this sum. In addition to this sum output, sum adder output, I want to generate ngCB, that is carry flag. Right? For example, this one is C, carry flag, which is this carry flag. So okay, so we assume adder is there, that adder, and then this adder, only that adder is there. Okay, and then this one, what is this? This one is B or inverted B, depending on this control signal. So that is covering that part. Right? B or inverted B. B or inverted B. B or inverted B. Okay. Then SLTU, right? SLTU, that is corresponding to this one. I think this one, right? So the thing is, so in hardware design, you can design this component, okay, in language, Verilog, and this component in language. Then if the wire name is the same, wire name, right? B2, that means that is connected. Okay, wire name is the same. This B2, wire name, this wire, 전선 name, right? 전선 is same, then connected, right? And SLT, that is not shown in schematic diagram. SLT, okay? SLT, that is not shown. Any question about hardware design? So pretty intuitive, right? So not that hard to understand. Okay. So so I try to follow. I'm following this encoding. So depending on these control signals, ALU, this ALU is generating right output, right? Generating right result. Okay. So that is ALU design. Okay. That ALU design. So now let's talk about this control signal generation logic, including ALU control. That ALU control. So that is the truth table. Once you have ALU control signal determined, okay, ALU control signal, right, like this. Yes, ALU control signal determined. Then you have to create another truth table like this. Okay, truth table to generate that control signal. So input and output. Now someone should generate that output control signal depending on operation code. Instruction is coming in, then based on that you have to generate that control signal, right? So now look at this table, right? So addition operation. If instruction is addition, Okay? How do you know if addition operation? By looking at these three. OP code, function 7, function 3. Then I'm talking about this ALU decoder, right? ALU decoder supposed to generate 5 zeros. 5 zeros. And add I instruction, same thing goes too, right? Add I instructions. So it is like truth table, right? In digital logic design, what steps did you take before you draw schematic diagram? Truth table, right? First, input output, relation, right? Then using K-map, Kano map, or Boolean, some other means, you can come up with Boolean equation. Using Boolean equation, you can draw, schematic diagram, right? So same thing, right? So here, truth table, input output relation, right? Inputs are OP code, function 7, function 3. Output ALU control. Okay. So if you look at this, branch instruction, by looking at this OP code and function 3, okay, okay, it is PQ. Then probably you have to ask ALU to do subtraction. Okay, or subtraction, right? So subtraction in case of branch. Okay, and then what else? Memory read instruction, LW instruction, for example, right? And you have to ALU to do addition operation to compute memory location, right? So here, by looking at operation code, right? You can tell. Okay, that is memory read. X means what? X means what? Don't care. I don't care. Don't care. I don't care. I don't want to look at function 7, function 3. Don't care. Right? If you look only OP code, then I can make that decision, ALU output decision. All right, there is one yellow code. Okay, now let's I like you to help me to determine this control signal. This is a practice. These control signals are determined based on the instructions, right? So in case of R-type instruction, think about R-type instruction. Think about addition instruction. Addition X4, X5 example, right? So that example. In case of R-type instruction, that instruction is inside CPU. Then can you help me to fill up these rectangles? R-type instruction example. Okay. Reg write should be what? Should be 1 or 0. Register write control signal should be 1, right? So after addition operation, X3 register should be updated, right? Should be 1. ALU source. Okay. Name is very intuitive. Second source of ALU. Second source to ALU. First input, register file output, or sign extended immediate. Which one? ALU source. In case of R format instruction, second source, X5, is coming from register file. So should be 0 to select first one, right? So BEQ, now BEQ control signal. Is it branch instruction, R type? No, right? Should be 0 or 1? 0, right? Memory write. Memory write, that signal is controlling memory update operation, right? Should be 0 or 1? Should be 0, right? You're not supposed to update memory, right? You are updating only register file, right? Should be 0. Mem to reg. Name also intuitive. Which one do you want to send to register file? ALU output to register file, or memory output, mem2reg, right? Memory to reg, mem2reg. Which one? So in case of addition, should be 0. To select first one, ALU output to register file. ALU control depending on operation code, OP code, and function 7, function 3. Okay, ALU control signal will be determined. Okay, how about LW instruction? Memory read instruction. X3 example. 16. Okay, decimal. X4. Okay, X4 plus 16 from that memory location. Okay, read data from that location. So think about that LW instruction. So reg write should be 1 or 0. Do you have to update register file? Yes, right? 1. AL source. Which one do you want to select? Register file output or immediate? Immediate, right? Immediate, right? So 1. Is it branch instruction? No, 0. Memory write. Do you have to update memory? No, you are reading from memory. Reading, right? Should be 0. Mem2 reg. Which one do you have to select? So in this case, you have to select second input, memory data. So should be 1. ALU control. ALU supposed to do what kind of operation? Addition operation. Addition operation to compute memory location. Addition. Okay. How about store word instruction? Think about store word. SW, X3, same, right? X4. You are updating a memory with that data, right? Location, X4 plus 16. So that location, right? You are updating, okay, memory. Reg write control signal. Do you have to update register file? No, right? It should be 0. ALU source. Which one do you have to select? Second input, immediate. So should be 1. Is it branch? No, right? Should be 0. Should be 0. Memory write control signal. You have to update the memory? Yes, right? Yes. Store word, right? Store word, right? Should be 1. mem2 reg. Which one you have to send to register file? ALU output or memory data to register file? You have to be careful here. Which one do you have to select? This one should be 0 or 1. Actually, X, meaning don't care. I don't care. I don't care. Which one? ALU output, memory data, I don't care. Anything is okay because I'm not going to update. Right? I'm not going to update register file anyway. Send me any data. I don't care. Right? I don't care. Then ALU control should be addition, right? ALU supposed to do addition operation. Last one. BEQ, branch instruction. BEQ, X3, X4, this label L2. Okay. So CPU should do subtraction. Okay. Branch instruction. Do you have to update register file? No, right? Branch instruction may update program counter. This program counter, if branch is taken, not register file, right? So should be 0. ALU source. Which one do you have to supply to ALU? Output from register file. So should be right, this one, X4, right? Should be 0. Is it branch? instruction BQ, right? Yes, should be 1. Memory update. Do you have to update the memory? No, should be 0. Then mem to rec, this one. Which one do you have to select to register file? ALU output or memory data? I don't care, right? Because reg write is 0. I don't care, right? I'm not going to update register file anyway. Send me anything. And ALU supposed to do subtraction operation. So you can follow the same step for instructions. You have to add for the milestone. Okay, for milestone you can do the same thing. Okay, then that CPU is able to execute add I instruction. Okay, so then to examine that, you can add one row. Okay, one row to see if the current form of the CPU is able to execute that instruction. Add I instruction. Reg write control signal should be 1, right? Think about X3, X4, number 12, immediate, right? Think about this. Then ALU source, second source to ALU should be immediate, right? Immediate. Okay, this immediate should be selected, should be 1. Is it branch instruction? No, 0. Memory update? No, 0. Mem to write, mem to rec, sorry. This mem to rec should select first output. Okay, first one. ALU output. So should be 0. And ALU supposed to do addition operation, add I instruction. Okay, so control signals are determined based on instruction. Okay, how about JAL instruction, jump and link instruction? This CPU is able to execute JAL instruction? No, actually no, because if you look at this CPU, look at this program counter related logic. PC is selecting either first one, PC plus 4, or adder, branch destination, not jump destination. So for JAL instruction, jump and link, you have to add some hardware digital logic, hardware module like this. Remember from the previous lecture, we have program counter register, right? PC register, DNQ, okay, clock, and then there is program counter, right? PC register and PC 32-bit. There are 3 candidates, right? 3 candidates trying to update program counter, right? First one is PC plus 4. First candidate. Second, branch destination. And third, jump destination. So these 3 guys are candidates. They are competing for this same input. So you need, multiplexer. If you want to use one multiplexer, then 4 to 1 mux. You have to use 4 to 1. 0, 1, 2, 3. So that is connected here. And the last one is not used. It is not used. Okay, then output. So adding multiplexer means you need a control signal, right? Control signal, selection signal, selection. In this case, 2 bits. Right? You need 1, 2, 0. 0, 0, meaning then you are selecting first one, right? 0, 0, 0, 0, right? 0, 0, 0, 1, select, second one, 1, 0, like this, right? So we added, in this implementation, we added 2 multiplexers, each 2 to 1 multiplexer, 2 to 1. Okay, 2 inputs, 1 output, 2 inputs, 1 output. Okay, so first multiplexer, this one, selecting either PC plus 4, follow this line, or branch destination. And second, subsequent multiplexer is selecting this mux output or this adder. Is doing computing jump destination. Remember this one? 20-bit sign extended and program counter is added, PC. So jump destination, right? So for JAL instruction, we added that hardware modules. Okay, this one, branch, jump destination logic and multiplexer. And what is this for? This one, if you think about JAL, jump and link, right? You have to store return location to, in this case, right, foo. The first one, hardware should do 2 things, right? Jump destination computation, and then X1 register file update, return location, PC plus 4, right? Return location should be saved in this case, X1 register, right? So register file update should happen. So if you follow this line, that is connected to register file. Okay, so PC plus 4, that is PC plus 4 is supplied, should be supplied. Okay, so we added those, digital logic, digital, component. Then you have to add one control, signal, JAL output for that, because control signal is inserted, right? Control signal. So control unit supposed to generate one more control signal called JAL. So then, this table. So the previous slide didn't have this column, JAL column, but now we have one more column, JAL. Okay, because new control signal is added. For R format, memory access, branch and addition instruction, JAL control signal will be 0. Okay? But for JAL instruction, if instruction is JAL, that will be 1, like this. So if you think about JAL operation, jump and link operation, register file should be updated, right? Register file should be updated, right? Second, ALU source, we are not using ALU. Second source to ALU, right? For jump destination, if you look at schematic, we are not using ALU for jump destination computation because we have separate hardware, right? So we are not using, so I don't care. Supply any input to ALU. I'm not going to use it, right? DQ, 0. Memory update, no, right? It's not memory update instruction. Mem to reg, you have mem to reg is what? Mem to reg, you have to be careful. Okay, so if you go back to here, that control signal, right? Multiplexer control signal is generating output to register file. So you have to provide right control signals to select last input, PC plus 4. Okay, PC plus 4. So you have to be careful. Okay? So here I marked it, X, because I'm not using memory data. I'm not providing memory data. Okay, JAL instruction will forward PC plus 4 to register file. And ALU, I don't care, right? ALU is not doing any useful operation. ALU will do some junk operation, if instruction is JAL. And important thing is JAL supposed to be 1. The control signal supposed to be 1. Okay, any question so far? All right. Then real design, decoder design. Look at this. Okay, so first main decoder. Main decoder is generating mem2, reg, memwrite, BQ, regwrite, and so on. Those control signals. Look at this description. So first, main decoder input and output, right? We have 7-bit input. So input 7-bit code and output. Okay, output. So regwrite, AL source, mem2reg, memwrite, JAL, and so on. So I added these two. Okay, add more these two. Okay, for AUIPC and LUI instructions. And then look at this. Depending on operation code, 7-bit operation code, control signal is determined, right? This one. In case of this one is R type instruction OP code. 2 zeros, 1, 4 zeros. That is R type instruction OP code. So if R type instruction is the one, then control signal will be this one. And then look at this, control. Okay, same signal. And concatenation operation, this opening curly bracket, closing curly bracket. And these are, output, AUIPC, LUI, regwrite, and so on. So 1 bit each. So let me count. AUIPC 1, 2, 3, 4, 5, 6, 7 bit. Control, that is also 7 bit. Okay. So, this one, 0. So if R type instruction is the one, then 0, right? JAL will be 0, second. Memwrite will be 0. Mem2reg will be 0. AL source will be 0. Regwrite will be 1, according to this description. Okay, very simple, right? And ALU decoder description. Look at this. So we have 2 case statement. Do we have some? Oh, no, right? So OP code. Better to show you probably this one. Control. Because color coded here. ALU decoder. ALU decoder. Look at this. ALU. Talking about that ALU decoder. Okay, ALU decoder. Okay. So we have 3 inputs. Right? 3 inputs. Here. OP code, function 7, function 3, and 1 output, right? 5-bit output here. 5-bit output, ALU control. So look at the description. So case statement, depending on OP code, if operation code is this one, okay, I defined it. So this one, I defined it somewhere, not here. Okay, here, OP1, 7-bit. Okay, R format encoding, right? R format encoding. Okay, here. Then begin and end, right? Then you have to look at function 7, function 3, 10-bit, 7-bit, 3-bit. So I'm listing, right? Look at this, very intuitive, right? 10-bit, 10-bit is this one. Then there is what? That is, look at this, addition instruction. Addition instruction. So ALU control will be this one. 5 zeros. Okay, 5 zeros. Okay, 5 zeros. And function 7, function 3 is second one. 0, 1, 8 zeros. Then 1, 4 zeros, ALU control. Very, intuitive description, right? So this is the one. Okay. So if the instruction is I-type arithmetic instruction, I-type arithmetic, do this. If instruction is I-type load instruction, right? Then ALU control will be this one. Okay. Branch instruction, branch, then control signal will be this one. To do subtraction, B, MSB is 1, 0. Okay. So 1. So this control unit is what? Control unit is combinational logic. What is combinational logic? Outputs, right? Outputs are determined only by current input. So there is no storage, no flip-flop, right? Inside that module. Only AND gate, OR gate, those logic gate. So if you are curious, again, if you are curious about, for example, this main decoder, how that is implemented actually in digital logic, so you can do this. Leave only main decoder. Okay. Then make sure the module name is same as project name. Like this. Then do what? Then do RTL viewer. Some problem? What is the problem? Some syntax problem. Okay. Some syntax. What is that problem? Oh, I removed everything, right? Okay, I'm supposed to. So it is not defined. Stupid. Okay, let me copy this one. Okay. Let me copy PowerPoint because it does not have some parameter defined. Okay. Okay. In decoder, then RV32I system. Then pure. Okay, here. Okay, so let me remove RV32I system. Twice. Let's remove CPU system. Okay, so I have to remove this one. Twice defined. It is mess. Okay, off. Prune is not complaining this time. Okay. Okay, so this is one example. Okay, Quartus generated this schematic for the simple example. Okay, these output are determined based on OP code. Okay, OP code. So 7-bit meaning 2 to the power of 7, 128. So decoder 120 out, 128-bit output. It is using this decoder to generate this one. So you can do that experiment yourself. Okay, performance. Any question? Probably I have to show you a demo, simulation demo. Okay, so let me quickly do that. Even though we are running out of time. So to run simulation, so you got to simulation folder, right? Simulation folder, this one. So run model sim. Okay, then do what? Then change file, change folder here, change directory to that place. Sim. Okay, where is sim? Download, I think. Download. class project sim. Okay, because I already compiled Verilog everything. Okay, Verilog design. Then if you go into sim, then work, this work folder is there, right? So that work, I just changed folder, this work. Okay, so expand it, and then I compiled it, all the hardware design. What you have to do is you have to select test bench top module, which is this one, RB32i system test bench. Right click on it, run simulation. So it is a listing, okay? So test bench, you have, if you look at the design, test bench, right? Test bench, you have what? You have these, signals, clock reset, hex. Look at this, clock reset, hex. Those signals are listed here, okay? And then that is not that interesting. I want to look at inside the design, right? Like CPU, right? So I want to look at CPU. Then to check out the signals, right? Familiar names, right? Mem write, mem address, something like this, right? So program counter, right? Instruction. So right click on it, select everything, and add wave. Okay. So here, the selected signals are added in here, right? Then run simulation, right? So how to run simulation? Easy, right? Here in transcript pane, here run, type run, probably 1000 nanosecond. Okay, 1000 nanosecond is not enough probably. Okay, so run 10,000 nanosecond. Okay, so zoom everything. This probably these are interesting, right? Those signals, and it is showing all binary numbers, so it's hard to read. So select everything, change radix to hex. Much much better, right? Hexadecimal numbers. So look at this signal, for example, program counter PC. Program counter is incremented, right? Look at this PC 0 4 1 0, right? Incremented based on that the program, right? And then instruction. Okay, so location 0 PC location 0, then instruction is 4 0 0 machine code, right? 4 zeros 113. Location 8 4, instruction is this one. Okay, and you have to run this simulation after changing Verilog code to make sure your design is running okay, right? Probably next time I'm going to show some more demos, right? So because we ran out of time, I have to let you go. Any question though? Okay, I guess that's it for today. I'll see you next time. Okay, bye. Okay, thanks.